So I'm going to wait just a minute, wait for the buffer to catch back up. And as soon as I see my face, I'll know we're caught up. All right, there we are. So let me answer a question offline to somebody else, and then I'll start answering the questions I got asked today. But this is a question that's getting asked from North Campus, so give me just a minute. Okay, that's going to be a long question to answer, so I'm actually going to answer it after live stream. So, got a lot of questions today for the live stream. I'll start with Julia's question. She had a few targeted ones. The first one she wanted to talk about was question 65 on the homework. So let me share the desktop with you. Now, think about McGraw-Hill. This is really obnoxious. Basically, it's written backwards, like you would understand that. So it's asking you how you would take this product, this cis, this trans 2-methyl-2-pentanol, and make this compound here on the left. Now, reasonable person reads left to right. So the way you're probably actually thinking about this problem is, how do I take so I got stuff on here from last week. How do I take the cis version and convert it to this ester? So you're probably a little bit easier to understand if you look at it this way. If we start with this, how do we make this? Now, what we're going to take a look at here are what we're going to look at is the stereochemistry. So first of all, it's interested in the actual stereochemistry, which means that whatever we're working with, we need to automatically put ourselves with reagents that are stereospecific. So when it says what would be a good intermediate here, it's talking about, if we look at the top, what would be a good way to go from this compound on the right to the compound onto the left? Since we're looking for something that has an inversion of symmetry, first of all, we use context clues. We haven't talked about alkenes that much, so probably not the alkene. The tosylate is a nice stereospecific inversion center. So if we have a tosylate, we're going to proceed through an SN2, and if we do nucleophilic attack, we'll end up getting this, this inversion of symmetry. So that's a good possibility. The alcohol here, not necessarily a good possibility, because OH groups can go through SN1, SN2. Bromide and the other alcohol, they're both kind of the same way. So that's going to be my first guess here, is that we'd like to go through the A intermediate, because the tosylate, the OTS, is actually pretty specific. Now, watch me pick it, it says no. So that's correct. If we react this alcohol up here on the right with tosyl chloride, we'll get the OTS. And then how do we convert the OTS to the ester? Choose the best option for the precursor to the tosylate intermediate. Well, basically that would be the alcohol you started with. Wow, that's so weird. And here's an overview of synthesis. There's no work. This is just a recap. So I'm guessing the confusion on this question is that for some weird reason they've got this written backwards. You would typically look at it right to left. So how do we go from the right compound and go to the left? Well, we take our alcohol, react it with a tosylate, and then react it with this nucleophile here. So that's question 65. Question 78. Select the combination of alkyl bromide and potassium alkoxide that would be most effective in the synthesis of the following ester. Why are there questions about esters in this? We're going to drop this question. So to answer your question, Julia, we're not going to do question 78. I don't know why it's asking about esters in the test chapter on alcohols and alkyl halides. The way I would answer this question is basically we need to create a Sorry, I want to see if I can figure it out. The way I would do it, I would start with a terp-butyl group and a methyl group. So the sec-butyl wouldn't work. The acetate wouldn't work. So we have the terp-butyl and the terp-butyl, so it's the option between A and B. Potassium methoxide is small, so you'd want to go with that, because a large base like potassium terp-butoxide, well, even both of those should work. Oh, that's just a bad question. So I'll get rid of question 78. Question 79. Also an ether question. I don't know why these ether questions are in this chapter. So we'll get rid of question 79 as well. Okay, so questions 24 through 26. Reacting 2R to pentanol with HBr leads to the formation of equal amounts of 2R to bromobutane and 2S to bromobutane. Draw a stepwise mechanism for the reaction that is consistent with this observation. So if we start with a stereospecific reagent and we end up with a racemic mixture of both the R and the S, this tells us we went through a carbocation intermediate. So when we do our carbocation intermediate, we're going to start by protonating the OH group and forming the H2O. That's going to pop off. And this will leave us with the carbocation. 2, 3. And just so it's a little bit easier to see what I'm doing, this doesn't actually change the answer by having it go up or down. So we put the carbocation on that carbon, save and exit. First step here in the mechanism is going to be create the carbocation, which will pop off. This will be your SN1 mechanism. What? Oh, jumped the gun. First thing we're going to do is form our OH2 group. My mistake. First thing you're going to do is protonate that OH group, and it's going to leave you with a bromide. What? That is absolutely correct. So you have the OH group attacking the hydrogen, hydrogen breaking the bond with the bromide. Hold on. I get unlimited submissions. So for this mechanism, you're going to have the oxygen, lone pairs attacking the hydrogen, and then breaking the HBr bond to give you bromide. Your reactions, remember the electrophile next file. Yes, I've done that. Oh, seriously. You've also got to keep the stereochemistry in there. Okay, so first step is you have attack of the oxygen on the hydrogen, breaking the HBr bond. This leaves you with the OH2 plus and a bromide. For the next step, we break a carbon-oxygen bond, and we create the carbocation. Oops, forgot to select the product there. So from the carbocation, we are going to have attack from the lone pairs of the bromine onto the carbocation, and that'll be our full mechanism. So that's the answer to question 24. You have a few questions. For Orgo-2, it's actually, today, it's going to be the reduction of benzophenone. I think there was a bit of a mix-up. This week, the lab was for Orgo-1 was preparation of diphenylacetylene, but for today, it's reduction of benzophenone. So let me correct that in case it is an issue on Blackboard. Yes, it is an accidentally copied and pasted the link for the Orgo-1 update for labs. So this week it is reduction of benzophenone. That should go a little bit easier for you. Next semester, Orgo-2 is going to be doing preparation of diphenylacetylene, but not this semester. Also looks like I'm having someone with technical issues on test 3. So let me take a look at that really quick. And also feel free to ask questions while I'm trying to work this out. 50, 51, 53, and 54. Yeah, so I'll get to that in just a minute. I want to make sure it's actually assigned my exams. That's assigned. All right, questions 50, 51, 53, This is also an ether problem. So, for question 50, what's the structural formula of the principal organic formed in the reaction of methyl bromide with potassium ethoxide? So, what's going on in this reaction? Get ready, question 50. Is we have nucleophilic substitution. So we have our potassium ethoxide, and we have our methyl bromide. So what's going to happen is our ethoxide is going to attack our carbon, and we're going to get displaced into the bromide, and we're going to end up with an ether when we're done. So the final product here, I'll switch to the desktop, is we have the ethyl, bridging oxygen, and the methyl. Definitely not what I put. We end up getting that ether. Question 51, I'm guessing is the same vein. Write the structural formula for the principal organic product formed with the reaction of methyl bromide and sodium benzoate. This is also a nucleophilic displacement reaction. So this lone pair here on oxygen is going to displace the bromine on the methyl bromide. And we draw it out. So we have our oxygen, and the oxygen here next to the sodium is going to displace the bromine in the methyl bromide to give us methyl benzoate. And give us that product. 53 and 54. Fischer protection of 2-bromooctane is shown below. Write the correct atom or substituent and contains formula prep box for the Fischer protection of the -2-ethanol. So, that's an odd question. Be in here. So this plus or minus is going to be synonymous with the RS. So if we want to flip R and S, the only thing we have to do is switch left-right. So for the A group, if we just do the CH3, bottom one, CH, what are you doing? CH2, and we can do, seriously. That's what I get for not reading and following all directions. So for the A group, CH3. For the B group, we just switch it with the hydrogen. For the C group, it's that obnoxious CH2. CH2. 4. CH3. And the last one's going to be Br. So basically when we do this to switch between plus and negative, it's just the same thing as switching between R and S. We just need to flip the H and the Br, so the Br will be in the D position, the H will be in the B position, A and C are the same. How are you possibly marking that wrong? Oh, because they're talking about substitution. We'll get rid of that question. That's a weird question. Question 54, and then what is the date of the third exam? If I remember correctly, it's next week. Yes, if you are in 252, next Monday your third exam starts, and it will be due the following Sunday. So, question 54, draw a stepwise reaction for the product following substitution reaction. Again, this is just nucleophilic attack. So we have our oxygen attacking the carbon, and then breaking that iodine bond. Your final product here is just your ether. Oh, yeah, you displace an iodide. So with these problems where you have like a small anion, particularly like something like an ethoxide or a methoxide, what you're getting is nucleophilic substitution. So you're used to alcohols where the alkyl halide is displacing the alcohol. The ethoxides, these are the reverse. This is where you have an oxygen displacing a halide. Now, if you work with small bases, so primary alcohols or alkoxides, those will do substitution. Big bulky bases like tert butoxide and propoxide, tert butoxide and isopropoxide, those typically engage in elimination reactions. So that help you at all, Elijah? It's kind of the same thing being done over and over again. You have this nucleophile, either an ethoxide, which has an O negative, or an alkyl halide, or a halide that has that like Cl minus or Br minus, and that's attacking whatever oxygen or a halide is bound to a carbon. Are any of those ether problems going to be on the exam? No. The reason why, so it's coming back to me now. The reason I assigned the ether problems is to get you two things. One, to get you out of this mindset that halides displace alcohols, but not the other way around. To get you thinking more about nucleophiles as like a concept. So typically any anion is going to be a good nucleophile, and it's going to participate in substitution. There are some weird ones, like I'm going to get rid of the one about it's calling it a Fisher projection. Well, yeah, that Fisher projection problem I'm going to get rid of because it's kind of a weird one. I didn't appreciate the wording on it. But I'm probably going to leave the ether problems in there because, again, I want you to lose this mindset of thinking that only alkyl halides, their anions, are nucleophiles. And to kind of get out of the mind, also to recognize that, yes, alcohols, when you deprotonate them to form the alkoxides, those definitely can serve as nucleophiles. And these even show up in the practice packets on the problem where I think the harder ones are where you start making these cyclic molecules. But on the exam, I wouldn't give you anything that difficult. Any other questions before I start answering all these weird questions I'm getting in Teams right now? Do 61. So question 61, draw the structure, including stereomeister, of compounds A and B in the following sequence of reactions. So compound A, this is tausyl chloride. It's going to be a nightmare, but you can definitely draw it. So the bigger challenge here is that we've got to build this stupid thing. So if we look at, so we've got this chair conformation, they're on opposite sides, so they're both equatorial. That makes them trans. And I'm going to do the tert butyl down here. Oh, stop it. Just punish students who go quickly. I know, this is a lot. So this is my guess for the first one. The big thing here is going to be the stereochemistry. And again, these should be trans. They're on opposite sides of that cyclohexene ring. Oh, you're going to be obnoxious, aren't you? Yep. Hold on. I've got to delete that oxygen. Make that nitrogen positive. Make that oxygen negative. So this is your tausyl complex, and I'm going to be really annoyed if this isn't correct. And then the lithium bromide here, we're going to displace the tausyl group, and we're going to get an inversion of symmetry. So instead before where these were trans, these are now going to be cis. Oh, stop it. And if it's not right, we're going to go check. Yeah, okay. So the challenge with part one is just drawing this stupid full tausyl chloride complex. But again, you can see it here. We've got Our compound starts out as trans with the OH, and our tosyl group here is just going to replace the hydrogen on the oxygen to give us the OTC, OTS, whatever the abbreviation for tosyl is, and then we're going to displace it with a bromine. Yeah, but I think the challenge of that problem is just that there's just a lot to draw. You're welcome. Any other questions out there? Now, Oregon 1, do remember that y'all do have your exam this week. So do shoot me an email if you're having issues getting the exam open. I've already got one saying the students had issues. Now to the emails. All right. Got another 15, 19 minutes for any questions that show up. Forgot how hard this is to do in a chair. All right, so see you all on the live stream tomorrow. Again, feel free to email any questions you have in advance. And those of you taking the exam this week, good luck. Those of you taking the exam next week, good luck.